Hi everyone, and greetings from Ithaca, New York. Like all of you, we've been forced to reconfigure lab experiences for our students due to COVID-19. In this video, I'll tell you about our online and hands-on lab activities for our Mechanics of Materials course. Our regular Mechanics of Materials course in the MAE department at Cornell is a 14-week course with approximately 35 total lecture hours and 4 in-person labs. We've also been offering it as an accelerated summer course with about 30 total lecture hours and 3 in-person labs spread over 6 weeks. This summer, we got approval to continue offering the course for lab credit by redesigning the lab experience for remote learning. We designed 3 lab activities in a scaffolded sequence, working towards more autonomy and higher expectations as the course progresses. In addition, some learning goals of the original fracture toughness lab will be addressed through a simple in-class activity with data collection, but no lab report component. The new ABET assessment scheme requires us to establish performance indicators for students' ability to design experiments, so we had already been making plans to shift away from traditional recipe-based lab activities. I believe the scaffolded sequence, together with the challenge of doing precision experiments without expensive equipment, are helping us to achieve learning goals that we weren't able to achieve with our traditional labs. Our hands-on labs require material kits which were mailed to students during the first week of class. I have 2 students overseas, so we didn't expect their materials to arrive in time for the first lab. So the first lab is a video demonstration and data analysis activity about heat treatments of aluminum and steel. Students watch a few pre-recorded videos showing the lab procedure with voiceover narration and then perform analysis on pre-collected data. I took advantage of the modules layout in Canvas, our course management system, to guide students through an introduction and an auto-graded pre-lab quiz so that they could show up to the virtual discussion and Q&A session prepared. The primary goal of this lab is to establish standards for what a good lab report looks like and give students feedback on their presentation of data. A lab report template was provided with a mostly written procedure. Students had to complete the procedure and then write the intro, analysis, and conclusion sections. In the next lab activity, students will set up and perform a load-controlled tension test and a constant load creep test on a nylon filament. The students first learn about the difference between load control and displacement control and see why displacement control is more difficult to achieve at home. The kit includes the nylon sample and a few basic supplies like S-hooks, picture-hanging nails, and a cheap spring scale, but students need to supplement these materials with items from around the house in order to perform the experiment. Rough directions are included for performing the experiment, but the students have to write their own detailed procedure. In my example, I suspended the filament from a stiff door frame and used a curtain rod lever to amplify the measured displacements. There are many ways to apply and remove the known loads. For example, I used a measuring cup to add rough amounts of rice to a load bucket while measuring the mass of the remaining rice on a kitchen scale. A student who beta tested the experiment for me pre-assembled 50-gram bags of beans that could be easily pierced and hung from a hook. In this way, the students are given a little bit more autonomy over the details of the experiment, and they have to write a detailed procedure in the lab report. The nylon fishing line is cheap, easy to work with, and flexible enough to produce easily measurable displacements over a gauge length of about 1 meter. The simple home experiment gives an approximate modulus that can be compared with literature values. Furthermore, fishing line could be purchased from hardware stores, which were still open even under the state of New York lockdown order. Although everyone performed nominally the same experiment, there was considerable variety in methods for measuring and applying the fixed loads. For example, here's one student's solution using pre-made bags of dry bulk foods. The creep experiment is essential for students to be able to analyze and interpret their stress-strain curves. Many students discovered during the first experiment that their measured stiffness depended on the rate at which they performed the test, and they correctly predicted the trend for faster or slower loading rates after completing the creep test. In the third lab activity, students design and conduct their own experiment to measure the Young's modulus of a steel wire. The 19-gauge wire is much too stiff to test in tension, but the students spend the first weeks of class learning to use Castigliano's theorem to find stiffness of structures. The students are allowed to plastically deform the wire into a shape more amenable to testing. Some possible examples are shown here on the left. Students also have a variety of options for how to measure the stiffness, either by measuring the deflection under a known load or by measuring the resonant frequency with a known mass. 2 student experiments based on coiled geometries are shown here on the right. Students design every part of the procedure, including designing the fixture and measurement method, estimating the maximum load they could apply based on the failure criteria they learned in class, and estimating the measurement uncertainty. This experiment involves the greatest level of autonomy. The students submitted a rough experiment proposal and then received feedback from me and the teaching assistant before refining and conducting their experiments, so we continued to provide support even as the activity became more open-ended. Students came up with a lot of solutions based on cantilever beam bending, coil spring extension, etc. One group even measured the frequency of a torsional pendulum hanging from the straight wire rather than measure the stiffness directly at all. During class, I also demonstrated several types of mechanical tests using household materials. Here, for example, I'm performing a single-edged notched beam fracture toughness test on a piece of cheese. Although the results could hardly be considered valid, it was a fun way to teach students about ASTM test specifications and interpretations of experimental data. I almost always require students to make some sort of prediction before the test using Zoom polling or some other classroom response system. In this case, I'm demonstrating a brittle helical fracture in a carrot as part of a unit on stress transformations and principal stresses. For a final optional assignment, students were asked to make a short video explaining and demonstrating a common ASTM standard mechanical test using household materials and supplies. Many students chose to continue our informal class tradition of testing food. You can see here a Brazilian indirect tension test on a zucchini, a 3-point bend test on chocolate, and a single-edged notched beam specimen made of a carrot. One student even baked cookies in the shape of Sharpie impact specimens and then progressively over-baked them to turn them into charcoal. Students had a lot of fun with these videos. I recommend providing some specific structure by curating a list of ASTM standards to use and a list of topics that need to be addressed. So for example, I required my students to discuss the specimen geometry and the reasons behind it, the measurements taken during the test and the properties calculated from them, and some of the requirements a test must meet to be deemed valid. But I otherwise encourage you to leave the assignment open for students to explore their own creative ideas.